In this video we study a powerful primitive in distributed computing, the so-called shared coin. We show how to use standard cryptographic tools like signatures and hashes to implement a shared coin, and then we use this shared coin to solve a difficult agreement problem. Let's start with the definition of a shared coin. Nodes in distributed systems often need to make random decisions. Each node can generate randomness independently, but how can the nodes make the same random decision? What we would like to have is the following. All nodes that make up the distributed system together run a distributed protocol to make a random decision, and the outcome of the random decision is 0 or 1, both with constant probability. We call such a protocol a shared coin protocol. Note that the two probabilities do not necessarily need to sum up to 1, which means that the shared coin protocol may fail. However, it can only fail with constant probability, so regardless of the probabilities, it only takes a constant number of trials until all nodes together create a random coin toss successfully. Now we understand what a shared coin is. As mentioned before, the plan is to build a shared coin protocol using standard cryptographic tooling. A digital signature attached to a message enables the recipient to verify that the message is indeed from the expected sender. Moreover, any change to the message would further invalidate the signature. So if the signature is valid, the recipient is also certain that the sender signed exactly the message that was received. The second building block is a so-called cryptographically strong hash function. When this function is applied to data of any size, it produces a fixed size output. When a party receives a hash, it is computationally infeasible for the recipient to find an input that produces exactly this hash. This property is called collision resistance. Moreover, cryptographically strong hash functions also have the property that the hashes look entirely random. In other words, it is not possible to reliably distinguish between hashes produced by such a hash function and random bit strings produced by a random oracle. Armed with these tools, we can now build a shared coin protocol. In this video, we only consider synchronous networks where all communication happens in fixed rounds. It is guaranteed that all messages sent in a round are also received in the same round. In the first step of our protocol, each node broadcasts a message, namely the current round number, R. Each message is signed by the sending node. Once all messages have been exchanged, the nodes have a list of all messages including the signatures. After verifying the signatures, all messages are hashed. The hashes are then interpreted as large numbers and the smallest of these numbers is determined. The outcome of the shared coin toss is then simply the lowest order bit of this hash value. If we assume that there are malicious nodes that aim to disrupt the shared coin protocol, what can they do? In the example here, there is a single malicious node. Under what conditions can it cause the shared coin protocol to fail? If we assume that nodes can only derive one valid signature for a given message, malicious nodes have no influence on their hash value. They can merely choose not to send it. If another node produces the smallest hash value, all correct nodes will agree on the outcome of the shared coin toss regardless of the actions of the malicious node. However, it is possible that the bad node just happens to produce the smallest hash value. While it cannot alter the hash value, it can choose to send it only to a subset of the nodes. The nodes that receive the value will compute the correct outcome of the shared coin toss. What about the other nodes? What's the probability that they get the same result? This is a good opportunity to pause the video for a bit and think about this question. Press play again once you're ready to continue. Did you figure it out? The answer is that it depends on the second smallest hash value and on whether that is a malicious node too. Let's assume that V2 is the node that produces the second smallest hash and that it is a correct node. All correct nodes receive this hash value and there is a 50% chance that its lowest order bit is actually the same as the lowest order bit of the smallest hash value. In this situation, it doesn't matter whether or not the malicious sends its value, all correct nodes will agree regardless. Of course, the node with the second smallest hash value may also be malicious. In that case, we'd have to also consider the node that produces the third smallest hash value and so on. Since only a fraction of the nodes can be malicious, we get a good approximation of the success rate of the shared coin toss without considering this case. Formally, let the random variable c denote the outcome of the shared coin toss. the probability that it is either 0 or 1 can be bounded as follows. The coin toss always succeeds if a correct node produces the smallest hash, which happens with probability 1 minus f divided by n. The second term is the probability that a malicious node produces the smallest hash, a correct node produces the second smallest hash value, and the second smallest hash has the same lowest order bit as the smallest hash. We can then simplify the formula as follows. If less than a third of all nodes are malicious, we see that the success probability is greater than 7 divided by 9. Since both 0 and 1 are equally likely, we get that the probability that the outcome is 0 or 1 is greater than 7 divided by 18. We conclude that this simple mechanism implements a fairly reliable shared coin. Let's now look at an example use case for our shared coin. We are given a distributed system comprising 5 nodes. In the following, we assume that less than a quarter of all nodes can be malicious. Since there are 5 nodes, 1 can be malicious. The goal is for all nodes to agree on a single bit. In the example, 2 correct nodes start with value 0 and the other 2 start with value 1. In our algorithm, nodes broadcast their proposal in every round, and the proposed value is always their current value. We introduce the simple rule that every node always sets its value to the value that receives the most support based on the messages that it receives. The algorithm has 2 phases that alternate until a decision is reached. So, all nodes exchange proposals. The malicious node obviously does not need to follow the rules of the protocol. It can propose 0 to some nodes and 1 to other nodes, or choose not to send anything. Each node then checks if it received some value at least n minus f, that is, 4 times. Note that we implicitly assume that each node also sends its value to itself. If this is the case, the node proposes this value once more and then terminates, accepting this value as the outcome of the shared coin toss. As we can see here, no node received a value 4 times. However, the topmost node received value 0 3 times. Based on the rule we introduced before, this node now also supports value 0. In the second phase, the nodes broadcast their proposals again. Since many correct nodes now support value 0, the malicious node tries to act against this trend and proposes 1 to all but one node. Every node checks again if some value has been received at least n minus f times. If this is the case, this node simply keeps its current value. This is the case for the topmost node. All other nodes use the shared coin to force a random decision. If the outcome of the random coin toss is 1, the nodes also keep their current values. However, if the outcome is 0, they set their local value to 0. In the example here, we assume that the outcome was indeed 0, so the node in the bottom right changes its value to 0. Note that the outcome doesn't affect the other nodes because their current value is already 0. Now, we circle back to the first phase. All nodes send their proposals. The malicious node is still intent on disrupting the protocol by sending the value 1 to all nodes. However, all correct nodes now receive the value 0 4 times, so they all propose 0 one more time and terminate. As we can see, the execution was successful. Let's now show that the algorithm is correct, but that means we first have to define what properties the algorithm must satisfy. The first property is called agreement, which says that all nodes must decide on the same value at the end of the execution of the algorithm. The second property is called validity. The algorithm has the validity property, or more precisely, the all-same validity property, if the nodes are guaranteed to decide on a value if all correct nodes start out with this value. Lastly, the third property is called termination, which says that all nodes must eventually decide on a value. If the algorithm has these properties even if some nodes may show arbitrary, erroneous or malicious behavior, we call it the Byzantine agreement problem. Nodes that are faulty or malicious are called Byzantine nodes. Let's consider the agreement property first. Assume that node V decided on value xv, and, for the sake of contradiction, there is a node W that decided on a different value. Let's first assume that W decided on its value in the same round. Since both nodes must have received their values at least n-f times, each node must have received its value from at least n-2f correct nodes. However, assuming that f is less than a quarter of n, this implies that there must be more than n correct nodes, a contradiction. Let's now assume that node W decides in a later round. Since node V received its value at least n-f times, all other correct nodes receive V's value at least n-2f times, which is more than n-half. So, all correct nodes must set their value to V's value and propose it. It follows that all correct nodes will then receive this value at least n-f times, so it is impossible that there are n-f proposals for node W's value. This proves that all nodes must agree on the same value. As far as validity is concerned, if all correct nodes start with the same value, they will all receive at least n-f proposals for this value. In that case, they will propose this value one more time and terminate having reached agreement. Before we talk about the termination property, let's revisit the calculation of the success probability of the shared coin protocol. Since we assume that f is less than a quarter of n, we get a different lower bound on the success probability of 27 divided by 32. Let's now take a look at termination. In phase 2, a node uses the shared coin toss only if it did not receive some value at least n-f times. First, we assume that no correct node received a value this many times. In that case, all correct nodes use the shared coin and, as we just showed before, they all agree on the same value with probability at least 27 divided by 32. What happens if some correct nodes received a value at least n-f times? Note that if it is more than one correct node, they all must have received the same value that many times. The other nodes use the shared coin. The probability that the outcome of the shared coin toss is the same as the value that the other correct nodes hold on to is at least 27 divided by 64. If this happens, all correct nodes will have the same value. How many rounds does it take to terminate? After the initial phase 1, there is always a phase 2 with a shared coin toss, followed by another phase 1. In expectation, the shared coin is used at most 64 divided by 27 times. In total, the algorithm terminates in less than 5.75 rounds in expectation. It is worth pointing out the correct nodes reach the decision before sending their final proposal, so one round can be deducted to determine the expected number of rounds until a decision is reached. Let's summarize what we've learned. We defined the notion of a shared coin. We then showed how a simple shared coin can be implemented using signatures and hashes, followed by a discussion on how this shared coin can be used to reach agreement quickly in a synchronous network if less than a quarter of nodes exhibit Byzantine behavior. Thanks for watching.